Okay, let us recall what we did in the previous lecture. So we have defined first open set. What is the open set? If X is a metric space and G is a subset of X, if I want to say that G is open, then for every X belongs to G, there exists some neighborhood. For that I can say there exists some number R such that that entire neighborhood lies inside G. This is the definition of open set. Then we have defined the interior of a set, or interior point. First of all, we have defined. So when I can say the X is an interior point of a sub A, which is a subset of a metric space X, it has a same condition. That means there exists R greater than 0 such that SR of X, which will be a subset of A. If I want to say that this X is an interior point, if there exists some neighborhood of that point which entirely inside the point A, then this A, sorry, this X, it's called the interior point of the set A. Then we have defined the interior of A. Interior of a set. The interior of a set is denoted by interior of A, or this is the notation. It is a set of all points X belongs to A such that there exists R greater than 0 such that SR of X will be subset of A. So that means all those points which are interior points of that set. So it, in particular, I can say the set of all interior point forms an interior of A. Using this interior, we have proved that A is open if and only if A is equal to interior of A. This is the first result we have did for interior. Secondly, we have proved that the interior of A is the largest subset of A which is open. I can say it is the largest open subset of A. Also, we have proved that the interior of A is the union of all open subsets of A. So these are the results we have discussed in the previous lecture. In this lecture, we will going to discuss about some more quantity which we have discussed in the previous lecture, which I gave you as an exercise to do. So this was the exercise I have asked you to do. What was the exercise? Let us recall. Let X be a metric space. And A and B are the subset of X. Then prove that this quantity, that is interior of phi, is equal to phi. Interior of X is equal to X. Interior of A is equal to interior of A. And I have told you to what will be this space. You can put which sign you can put here also. And also what will be the A is a subset of B. Then it will imply interior of A will be a subset of interior of B. Now, the first is easy to see. Let us use the proof for that. So somebody from you guys are saying something about the first one. Why the first quantity, that is interior of phi, will be phi itself? Why it is true?
Interior of phi is phi, and phi is subset of phi.
No, that is not the reason.
Sir, phi is open, therefore interior of phi is equal to phi.
Yeah, phi is an open subset of X. We have proved that the empty set is the open subset of X. And in the previous lecture, we have proved that if A is open, if and only if interior of A is A. This was the result we will use here. So therefore, or not therefore, comma, interior of phi will be phi. Same way, second one is interior of X is X. Same reason. Since X is an open subset of X, so hence interior of X will be X due to the same reason, that is A is open if and only if interior of A is A. The third one was the interior of A is interior of A. So since, what will be the reason? Interior of A is always open set, that we have proved in the previous lecture. The interior of A is an open set. Hence, interior of A is equal to interior of A. So here this is the set A. So if I can say this is the set B, then interior of B is equal to B if this B is open, and we have the B is open here. So that's why this is also true. So first three statements are easy to see. Now from some of you have already discussed that here you will have this sign, that is interior of A union B is a superset of interior of A union interior of B. Why this inequality is not true, that you can give me example of that particular case. That means interior of A union B is not a subset of interior of A union interior of B. You need to give me example for that after I will prove this. So let us prove that statement, fourth one. So what you need to prove is this: interior of A union B is superset of interior of A union interior of B. So ultimately I have to show that this is the subset of this. So if I want to show that two sets are subset of each other, then I will put some point here, and how to show that that point will be in this. So I will start with, for any X belongs to interior of A union interior of B. This will implies X belongs to interior of A or X belongs to interior of B. Since interior of A is a subset of A, which is always there, and interior of B is a subset of B. From this, what we can say is your X is belongs to A and X, oh sorry, not and, but or X belongs to B. So this will implies X is belongs to A union B. I want to prove that it is not in A, it is in A union B, but I also want to prove that it is in interior of A and B. So now there will be two possibilities are there. Either X is belongs to A union B, or X is belongs to A. Sorry, either X is in the interior of A or X will be interior of B. That will be two situations we have. So we need to start with, let us suppose if possible that X is belongs to interior of A. So suppose that X belongs to interior of A. If it is belongs to interior of A, according to the definition of interior point, so I can say X is the interior point of A. As per the definition of interior point, there exists some R greater than 0 such that SR of X will be a subset of A. That we can say. But we will always has A will be a subset of A union B. So therefore we can say that there exists R greater than 0 such that SR of X will be a subset of A union B. So from this I can say that X is an interior point of A union B. Therefore X is belongs to interior of A union B. And similarly, if your X is belongs to interior of B, then also we have the same situation. So ultimately what we can say is X is, in any of the case, X is belongs to interior of A union B. So hence interior of A union interior of B will be a subset of interior of A union B. So this completes the things. Why? Now anyone have the example why this is not true? This will be not true. Anyone have any example for that?
Hello.
Yes.
If we choose A equals to Q and B equals to Q complement,
A is equal to Q and B is equal to Q complement. What is interior of Q?
phi.
Interior of Q is phi. Very good. And interior of B,
Also
which
phi.
it's also phi. Very good. So A union B will be Q union Q complement, which will be gives you R, the set of all real numbers. The interior of A union B will be R. Barabar?
Yes.
What is the interior of A union interior of B, which is phi? So that means this side is R that we have did here. And this side is phi. So phi, this will not be possible. So that's why the reverse side is not possible. This is the counter example for that. Very good. You did well. So this is the example for that the equality will never be there. Okay. Fine. Now those who have not understood why the interior of Q is phi, how many of you have understood that? You just look at the definition of the interior point and use the a theorem, rational density theorem, which you have learned in your analysis 1, that any point is there, x. If I want to say that if it is a rational point, and if I can take the neighborhood of that point, then that neighborhood always contains irrational points due to the rational density theorem. So therefore, this interval will never be lies inside the A due to it contains irrational points. So that's why this x is not an interior point. And the same argument, and this x I have taken arbitrary, any point. So that's why there is no point is there which are interior of that set. So that's why the interior of Q will be phi. And the same argument for given for Q complement, that is interior of Q complement will be phi. So that's completes that inequality will not be true. Next, we have the fourth or fifth one. The fifth one was to prove interior of A union B. Sorry, not union, but it was intersection. Union we already did. Intersection B is equal to interior of A intersection interior of B. So what was I have given you that what should be the sign you will have, but here you will have equality sign. Now we have to prove that two sets are equal. That means you have to prove that one will be a subset of other and other one will be a subset of. So this is the things we need to prove here. So first I will prove that this is a subset of this. If I want to prove that one set is the other, I need to start with any point will be inside the interior of A intersection B. So as per the definition, we can say that therefore there exists r greater than 0 such that SR of x will be a subset of A intersection B. But A intersection B is always a subset of A, and the same way I can say that it is a subset of B, because A intersection B is always a subset of A and A intersection B is always a subset of B. So that means this portion SR of x is common in A as well as in B. So hence we can say that x is an interior point of A and x is an interior point of B. So therefore x is belongs to interior of A and x belongs to interior of B. That will imply x is belongs to interior of A intersection interior of B. So this will prove that the interior of A intersection B is subset of interior of A intersection interior of B. We call it this is as a statement 1. Now the other way, we have to prove that this will be a subset of this one. So for that I will take one point in this set. So for any x belongs to interior of A intersection interior of B. This will gives you X belongs to interior of A and X belongs to interior of B. We note that this interior of A is always a subset of A. So this will imply X is belongs to A and X is belongs to B. Why? Because interior of A is always a subset of A and interior of B is always a subset of B. So this will imply X is belongs to A intersection B. So it is in intersection. Now we need to prove that it is in interior of intersection of A intersection. So here, as X belongs to interior of A, there exists some R1 greater than 0 such that S R1 of X is a subset of A. And X belongs to interior of B. This X is also in B, interior of B. So there exists some R2 greater than 0 such that S R2 of X will be a subset of B. Now what we will take? We'll take the whatever the value which is minimum out of this R1 and R2. So take R will be a minimum of R1, R2. So if this is a minimum, we can say that SR of X is a subset of SR1 of X and SR of X is a subset of SR2 of X. And this is already a subset of A. So hence we can say that SR of X is a subset of A and SR of X is a subset of B due to this. So this will imply SR of X is a subset of A intersection B because it is in common in A and B. So it is in intersection. So what we can have, what we can say is there exists R greater than 0 such that SR of X is a subset of A intersection B. That means this X is an interior point of A intersection B. So hence this X belongs to interior of A intersection. So therefore we can say that interior of A intersection interior of B will be a subset of interior of A intersection B. This is the statement number 2. So from 1 and 2 we have interior of A intersection interior of B is equal to interior of A intersection B. This completes the proof of that fifth statement. Now we have the next sixth statement, which we prove that A is a subset of B implies interior of A will be a subset of interior of B. So I will start with let X belongs to interior of A. I have to show that this is a subset of this one. This is given to you. I am taking one point here. I have to prove that that point will be into this interior of B. Since X is in interior of A, we can say that there exists R greater than 0. SR of X will be a subset of A. But what is there? A is subset of B is given to us. So therefore, we can say that there exists r greater than 0 such that SR of x will be a subset of A, which is subset of B. So this SR of x will be a subset of B also. So hence we can say that is x is an integer point of B. So therefore x is belongs to interior of it, which completes the proof of the sixth statement also. Now let us see some of the examples. If x is R with usual metric, so we are talking about usual metric. We say find the interior of the following sets. The first one, close interval 0, 1. Second one, Q complement, which we already did. Third one, the set of all points which are of the form 1 upon n such that n belongs to n. The fourth one is Z. Fifth one is close interval 0, 1, intersection Q. Sixth, Q, set of all rational numbers. Seventh, N, set of all natural numbers. 8, close interval 0, 1, union Q. So now let me discuss the first problem. What will be the interior of the interval close interval 0, 1? So here let me draw that interval. Close interval 0 to 1 is there. If I pick any point inside this interval, that means for any x is belongs to open interval 0, 1, we can able to draw one open neighborhood of that. So for any x belongs to this, there exists r greater than 0 such that x minus r to x plus r, which is subset of this in this set close interval 0, 1, which is I can write. So for any x we have this situation. Therefore, this all the points which are in open interval 0, 1 are the interior points. Now only 2 points we need to check, they are left. One of them is 0, another one is 1. So can you say that 0 is an interior point of this set? The answer is no, because if you can try to draw a neighborhood of 0, that neighborhood will not lies entirely in the interval close interval 0 to 1. It's in this portion is the outside. So that means 0 is not an interior point of close interval 0, 1. 1 will be the interior point of the close interval 0, 1. The same argument gives you answer no. An interior of a set is always a subset of the original set. So there is no other point you need to discuss. So here we should write, we note that 0 is not interior point of closed interval 0, 1, as we cannot find open sphere of 0 which is contained by closed interval 0, 1. Similarly, 1 is not an interior point of closed interval 0, 1. So final answer, the interior of closed interval 0, 1 will be open interval 0, 1. For Q complement and Q, I already explained you the reason. What are the interior of Q and Q complement? Yes,
5.
right, which I already discussed. Okay, fine. Now let's talk about the third example. So what is the interior of this set? Anyone want to say about anything regarding the interior of this set? Set of all points which are of the form 1 upon n, where n is a natural number.
Five.
5. So why it is a 5? Because if you can pick up any m belongs to n, then what will be the neighborhood of this m? The m minus 1 upon, sorry, it will be 1 upon m minus delta, and 1 upon m plus delta will be the neighborhood of the point 1 upon m. So can we say that it will be a subset of this set? I can write there does not exist any delta such that this will be a subset of 1 upon n such that n belongs to n. And this is true for any m in this set n. So therefore, the interior of 1 upon n, n belongs to n, is 5. It is an empty set. What about z? What about z? What you can say about this z? What are the interior of the z?
So 5.
It is also 5. Very good. Why? It was the fourth example. Na? So fourth example is z. The interior of z will be 5. Because for any x belongs to z, the neighborhood of x, which is x minus delta to x plus delta, I can say any neighborhood of x, which is of the form x minus delta to x plus delta, will contains, always contains rational and irrational numbers. Okay, because this is your z, 0, 1, here it is -1, 2. If I pick a neighborhood of 1, and this neighborhood, any neighborhood you can consider, it always contains rational numbers as well as irrational numbers. And this rational and irrational are not in Z. So this neighborhood will not lies inside Z. So hence, this interior of Z will be a 5. What about the fifth example? Use the result which we have did previously. That way also you can get. Previously we have proved this interior of A intersection interior of B is equal to interior of A intersection B. If you use this result, that will also leads you to solve this or to find out the interior of this set.
Sir, 5.
Yes. Because interior of closed interval 0, 1 intersection Q will be interior of closed interval 0, 1 intersection interior of Q. We don't want to use any argument. Then an interior of 5 we already calculated. Interior of closed interval 0, 1 we already calculated. 0, 1 open interval 0, 1, this is pi. So the finally you will have pi answer. What about n? I'm not giving you answer for that. You can try for yourself. It is similar argument as that we can give for n. What about the last example? That is union. And in the union there will be no equalities there. So you cannot use this argument which we have used here. Because we have seen that in the equality, sorry, for the union there will be no equalities there. What will be the answer? Just see the set. What will be the set? The set is closed interval 0, 1 with all the rational points outside this set. All the rational points which are exist there. What will be the interior of this set? So first of all, what will be the interior of this set? Closed interval 0, 1. Is all the points which are lies inside this interval. They are the interior point of the set, because if I pick any point here, if I draw open neighborhood of that, that will be lies in this set. So that's why any point on the closed open interval 0, 1 will be a interior point of this set. If I pick 0 and if I draw a neighborhood of 0, then this portion will also contain irrational numbers. This portion is always containing irrational numbers. So that's why 0 is not an interior point. Same argument will give for 1. If I pick up any rational number outside this interval, if I pick, let's say, a point p by q, the same argument, if I draw a neighborhood of this p by q, this neighborhood contains irrational points. So any rational numbers outside this interval will not be an interior point of this set. So that's why the only possibilities are this. So the interior of this set is open interval 0, 1. So this will be the interior of the set. Let me give you one more example. Now consider X as C, and my set is the set of all Z, which is of the form X plus Iy, such that X is between 0 and 1 and Y will be 0. So can somebody tell me what is this set represent first of all? So if I draw a x-axis and y-axis, it says first of all y is 0. Y0 is nothing but the x-axis. This is the line y equal to 0. And your x is between 0 and 1. So that means your x is from 0 to 1. So it will be the interval 0, 1. This set actually represents the interval 0, 1. But this interval is as a subset of C with usual metric I am taking over here. So C with the usual metric. What will be the interior of this set A? The question is, what is the interior of the set? So what is your argument about the interior of this set? The interior of this set, to calculate the interior, you have to draw a neighborhood of any point on this set. So if I have pick up this point X, and you know that the neighborhood of C will be disk. So if I have a disk here, and this portion which is not lies inside the set, therefore any point on this interval 0, 1 is not an interior point. So interior of this set will be a phi. So I can say that, in short, I can say that closed interval 0, 1 as a subset of C, its interior is phi, but as a subset of R, their interior is open interval 0, 1. So this is the difference between. So if you change your space, the interior will be changed. Let's talk the next definition. The next definition is about the limit point of a set. Let X be a metric space and if A is a subset of X, a point in X it's called a limit point of A if each open sphere center at X contains at least one point of A different from X. This is the definition of the limit point of a set. Limit point of a set A. What is this says? Suppose this is the set A, and if you want to say that this point X, it's maybe outside, maybe inside the set, we don't know. But for that, it says that if there is a point X is there, and if you can able to draw each neighborhood of this, so that's why it is each open sphere. Every open sphere should satisfy this condition. Every open sphere. If you can able to draw for each and every neighborhood of this, which intersection with this set and this neighborhood will be at least one point will be there, except different from X. So in the notation, it can be written as set of all X, sorry, SR of X minus X intersection with A is non-empty for every R greater than 0. For every R, because it says that for each and every open sphere center at X contains at least one point. So this intersection is non-empty, different of A, different from X. So that's why I will subtract X from this. So this is the definition of a limit point. Let us give you examples so this definition is clear in our mind. So I will take this as an example. Let's say this A set is close interval 0, 1, X is R with the usual metric. Question is to calculate the limit point of this set. So let us draw a line. Now the limit points are maybe outside also. It is also inside the set. We don't know. So you have to think for each and every point on the real line, because your original set is R. For example, I will pick any point on this outside this interval. Let's say this point is X. So can you able to draw one neighborhood of this, which is, I can say, X minus delta. What should be the value of delta you can choose, so that this interval intersection with A is empty. If you can get that such delta, if you can find out at least one delta, then this X will not be a limit point. Ultimately, this neighborhood and this A, except this point X, is empty, then we can say that this point X is not a limit point. And that we can get. What about 0? Let's say if I take the 0. If I draw a neighborhood of 0, any neighborhood of 0, then this portion is always common with A. So that's why 0 is a limit point of the set A. Same argument will give you for 1. Same argument will give for 1. So this is a limit point. Any point inside this interval, let's say x, if I draw any neighborhood of this, will you say that any neighborhood will having the intersection? Means you can pick any bigger interval, but this portion is always common in that. So that's why the intersection has to be at least one point should be there. Okay. So what are the limit points of this set A? The closed interval 0, 1 is the limit point of the set A. That is gives you argument how to write down. So here 0 is the limit point of A, which is in the set, this A. Also 1 is the limit point of A, which is in the set. Further, any point, any x which is in between this is also a limit point of A. Therefore, the limit points of A are closed interval 0, 1. Let us take another example, second. I am saying set B will be 1, 1 by 2, 1 by 3, up to so on. Here x is R with usual metric. What are the limit points of this set? So what will be this set? This set is 0, is not included in this set, but the set is 1, 1 by 2 is here, then it is 1 by 3, and so on. So can somebody tell me what will be the limit point of this set? Can I say, first of all, 1 is a limit point of this set? So as per the definition, you can, for every neighborhood of 1 except 1, there will be intersection with this. Is it there? So if we can try to draw a neighborhood of that, any neighborhood, and if we can accept minus this point, you have to remove this 1 from that interval. So this portion with this set B will not. So I can say that 1 minus delta to 1 plus delta, where the delta value of delta you can pick up less than 1 by 2. So if you can take this, delta will be less than 1 by 2. So this portion, any value will be between here, any neighborhood in between this. So choose your delta will be less than 1 by 2. So it is 1 minus 1 by 2 and 1 plus 1 by 2, whatever, will minus 1. Intersection with B is always pi. So I can say that therefore 1 is not a limit point of B. Same argument can be given for 1 by 2. In that your delta should be less than 1 by 3. At least if we can get 1, then we can say that it is not a limit point if the intersection is pi. So in fact 1 by 3. So any of the point 1 by n is not a limit point of this set B. What about other points? Can I say other points, that is if the point is here, will be a limit point of that set? Again the same argument I can be given, which is not, because we can have the one neighborhood, we can see that, which is not having intersection with B is pi. Can somebody think for other points? Now think for the point 0. Yes?
Sir, 0, we can find such neighborhood.
Yeah. So if you can have the neighborhood of 0, any neighborhood of 0, minus delta to plus delta, whatever the, for any delta, minus 0, if you remove that point from this, will always have intersection with B is non-empty. You can take any delta because this contains very small 1 upon n. If n tends to infinity, and this will goes to 0. So this any delta you pick, any interval you can pick, whatever the number you want to take, greater than 0. We all have this. So therefore we can say that 0 is a limit point of B. So the limit point of this set is only B. Next, third one, let's take this example Z, the set of all integers. So what are the limit point of Z? I want the answer from you guys. Think for the line 0, 1, 2, here on this side -1, -2. These are the points which are here. Can I say 0 is a limit point of Z?
No, sir.
No, because you can have the neighborhood of 0 which is not intersecting any point intersecting with Z. Same way 1 is not a limit point, 2 is not a limit point. What about the any point in between 1 by 2, 1 and 2? If I pick any point here in between 1 and 2, you can have a neighborhood of that also, having the radius, or I can say 1 by 2 as a its radius. So if I can have x minus 1 by 2, x plus 1 by 2 minus x intersection with this z is always pi. This interval never contains any integer. If x is not an integer, if x is not an integer, if x is not integer, then this is there, always there. So hence we can say that, what we can say? The limit point of z is pi. There is no point will be a limit point of z as a subset of R. Let's take the next example, Q, the set of all rational numbers. What are the limit points of rational numbers? What is your, here also I need the answer from you guys.
Sir, all the real numbers?
All the real numbers. Why? Because if you pick any rational numbers, in the neighborhood of that rational numbers, whatever the point is there, whether it is a rational numbers or irrational, if it is irrational number, then always there will be a rational number in between them. Okay. So this interval always contains rational and irrational numbers except this p by q. So that's why all the real numbers are the limit point of this Q. And same argument for given for irrational numbers. If it is a number is not of the form P by Q, so let's say that X is an irrational number. In the neighborhood of this irrational numbers, always have the rational numbers. So that's why by rational density theorem, we can say that the limit point of Q are all the real numbers. So we can say the limit point of Q are all real numbers. Let us change the metric. Let's consider this discrete matrix. D of xy is equal to 0 if x is equal to y, 1 if x is not equal to y. If I take, let's say, set any, if I take R, and in that I'll take the interval 0, 1. What will be the limit point of this set into this metric? So R with a discrete metric. I have not taken now here usual metric. I am taking a discrete metric. So what will be the limit point of this set? What is your answer? What you can think for this? So for that you have to look at what are the open spheres whose radius is less than 1, which we already discussed. So what will be the open sphere in this discrete space? So x, let's say x is in this A. What will be the S R of x? If this R is 1, if I quick pick this R is 1, then what will be this? The set of all, this x is, I'll take x0 here. So x is belongs to x such that d of x comma x0 is less than 1. So radius I have taken 1. So what will be the points possible here? What are the points possible here? There are two values of this d of x comma x0 is possible, either 0 or 1, and this quantity is less than 1. So only two possibilities there, either x is equal to x0 or x is not equal to x0. But here x is not equal to x0 due to this, due to this is less than 1, we can say that this distance is equal to 0. So therefore, the set of all x such that x is equal to x0. So this open sphere only contains its center. So S1 of x0 minus x0, because as per the definition of the limit point, you have to remove the center from it. Intersection with A is what? What is this?
So phi.
Phi, because you are removing, this is only a singleton point and you are removing that point from that, and the center A you have taken. So there is no point in this set which are the limit point. So can I give you same argument if x is not in A? Same argument. If x is not in A, there is no change in this. So I can say that if x0 belongs to R, then we have the same argument. So ultimately what we can say? There is no point of A. In fact, I can state it like this: there is no subset of R which has a limit point. So this is very, we can write no subset of R with discrete metric has limit point. There will be no subset of R which having a limit point. Why? Close interval 0, 1. You can pick any set. With the discrete metric, you can take any. Instead of R, I can say any metric you can, sorry, any space you can have. Why R? You can take any space. That does not have any limit point. Okay, so this is, if you change your metric, then also the scenario will be changed. In the previously with usual metric, the limit points of this sets are close interval 0, 1. But if you change the metric, it is nothing. So that's why if you change your metric, if you change your space, the scenario will be changed. Okay, so I will stop here. If you have any problem, you can ask. You have not understood anything, you can ask me.